For over 30 years, a telescope the size of a school bus has been floating in space, 550 kilometers above Earth. NASA's Hubble telescope has taken more than 1.5 million photos of the universe, and each one has changed the way we understand everything around us. It has shown us galaxies being born, stars dying, and places so distant that their light took 13 billion years to reach us. But here's the most impressive part. Hubble discovered that the universe is growing faster and faster, and nobody knows exactly why. Over the next 2 hours, you'll see the most incredible discoveries ever made by this space telescope. From planets outside our solar system to giant black holes at the center of distant galaxies, every image you'll see is a window to the past, showing how the universe was millions or even billions of years ago. Subscribe to the channel, leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Have you ever wondered what would happen if we discovered that everything we thought we knew about the universe was completely wrong? Well, that's exactly what happened when the Hubble Space Telescope made one of the most shocking discoveries in the history of astronomy. Scientists expected to find that the universe's expansion was slowing down due to gravity, but instead they discovered something that turned our understanding of reality upside down. Back in the 1990s, 2 teams of astronomers were using Hubble to study distant supernovae, specifically type Ia supernovae, which are incredibly useful because they always explode with roughly the same brightness. Think of them as cosmic light bulbs that always shine with the same wattage no matter where they are in the universe. This makes them perfect for measuring distances across cosmic scales, because if you know how bright something should be and you can measure how bright it appears, you can calculate exactly how far away it is. The teams were led by Saul Perlmutter, Brian Schmidt, and Adam Rees, and they were originally trying to measure how much the universe's expansion was slowing down. Everyone knew the universe was expanding since Edwin Hubble's discoveries in the 1920s, but the big question was whether it would expand forever or eventually collapse back on itself. The answer depended on how much matter was in the universe and how fast the expansion was decelerating. But when they started analyzing the data from dozens of distant supernovae, something didn't add up. These distant explosions appeared dimmer than they should have been if the universe's expansion was slowing down as expected. At first, the teams thought there might be dust in space making the supernovae appear fainter, but careful analysis ruled that out. The only explanation that fit the observations was mind-bending. The universe wasn't slowing down at all. It was speeding up. This discovery was so unexpected that both teams spent months double-checking their work, looking for any possible error. They analyzed their data over and over, considered alternative explanations, and even competed with each other to make sure their results were correct. But no matter how they approached it, the conclusion was the same. Distant supernovae were indeed fainter than expected, which meant they were farther away than they should be in a decelerating universe. What this meant was that in the time it took light from these ancient explosions to reach us, space itself had expanded more than anyone thought possible. The galaxies hosting these supernovae had been carried away from us not just by the initial expansion of the universe, but by an additional acceleration that was stretching space at an ever-increasing rate. The implications were staggering. If the universe's expansion was accelerating, there had to be some kind of force or energy causing this acceleration. But what could possibly overpower the gravitational attraction of all the matter in the universe? After all, gravity should be pulling everything back together, not pushing it apart. Scientists had to invent an entirely new concept to explain what they were seeing. They called it dark energy, and it represents one of the biggest mysteries in modern physics. The name dark doesn't mean it's necessarily black or invisible in the way we normally think of darkness. Instead, it means we can't detect it directly through any known means except for its gravitational effects on the large-scale structure of the universe. Based on Hubble's observations and subsequent studies, dark energy appears to make up about 68% of everything that exists. That means more than 2/3 of the universe consists of something we can't see, touch, or directly measure, but which is powerful enough to accelerate the expansion of space itself. Regular matter, the stuff that makes up stars, planets, and everything we can directly observe, accounts for less than 5% of the universe. The rest is dark matter, another mysterious component that we can detect through its gravitational effects but can't directly observe. The discovery of dark energy completely changed our understanding of the universe's fate. Before this discovery, cosmologists debated whether the universe would expand forever or eventually collapse in a big crunch. Now we know that not only will the universe expand forever, but it will do so at an ever-increasing rate. This has profound implications for the far future of cosmic evolution. As space continues to accelerate its expansion, galaxies will become increasingly isolated from each other. Eventually, galaxies beyond our local group will disappear beyond our observable horizon, carried away by the expansion of space itself. In the very distant future, trillions of years from now, observers in our galaxy would see a universe that appears almost empty, with only the gravitationally bound objects in our immediate cosmic neighborhood remaining visible. But the story doesn't end with just measuring this acceleration. Hubble has continued to refine these measurements over more than 2 decades, providing increasingly precise values for how fast the universe is expanding and how that expansion rate has changed over cosmic time. These ongoing observations have revealed that the acceleration wasn't always happening. For the first several billion years after the Big Bang, the expansion of the universe was indeed slowing down, just as scientists expected. The transition from deceleration to acceleration happened relatively recently in cosmic terms, about 5 to 6 billion years ago. This timing isn't coincidental. In the early universe, when galaxies were much closer together, the density of matter was high enough that gravity could overcome the effects of dark energy. But as the universe expanded and matter became more diluted, dark energy began to dominate, eventually causing the acceleration we observe today. Understanding this transition has been crucial for developing theories about what dark energy might actually be. The leading candidate is something called the cosmological constant, a property of space itself that Einstein originally introduced in his equations of general relativity. Einstein later called the cosmological constant his greatest mistake when he learned that the universe was expanding, but it turns out he might have been right after all, just for different reasons than he originally thought. The cosmological constant suggests that empty space itself has energy, and as the universe expands and creates more space, it also creates more of this vacuum energy. This energy doesn't dilute as the universe expands like matter does. Instead, its density remains constant, which means its total influence grows as the universe gets bigger. This could explain why dark energy's effects have become more prominent over time. However, there are significant problems with this explanation. When physicists try to calculate how much vacuum energy space should have based on quantum mechanics, they get a number that's either zero or vastly larger than what we observe. This discrepancy, known as the cosmological constant problem, represents one of the biggest unsolved puzzles in theoretical physics. Alternative theories propose that dark energy might not be a constant property of space, but could instead be a dynamic field that changes over time, similar to other fundamental forces in nature. These theories, often called quintessence models, suggest that dark energy could strengthen or weaken as the universe evolves, potentially leading to different outcomes for the universe's ultimate fate. Hubble's continued observations are crucial for distinguishing between these different possibilities. By measuring supernovae at various distances and therefore at different points in cosmic history, the telescope can map out exactly how the expansion rate has changed over time. These measurements can reveal whether dark energy has remained constant or has evolved, providing critical tests for different theoretical models. The precision of these measurements has improved dramatically since the original discovery. Early studies could only determine that the universe was accelerating, but now Hubble can measure subtle changes in the acceleration rate and compare the expansion at different epochs with incredible accuracy. This has led to increasingly stringent constraints on the properties of dark energy and has ruled out many theoretical models that seemed plausible when the acceleration was first discovered. One of the most important aspects of this work is that it requires observations of objects at vastly different distances, corresponding to different times in the universe's history. Nearby supernovae show us how the universe is expanding now, while distant ones reveal how it was expanding billions of years ago when their light first began its journey toward Earth. By comparing these different epochs, astronomers can trace the history of cosmic expansion in remarkable detail. The impact of this discovery extends far beyond astronomy. It has influenced fundamental physics, philosophy, and our basic understanding of reality. The fact that the vast majority of the universe consists of mysterious dark energy and dark matter means that our direct experience of the world around us represents only a tiny fraction of what actually exists. This has humbling implications for human knowledge and suggests that there are still profound mysteries waiting to be discovered. Moreover, the techniques developed to study dark energy have found applications in many other areas of astronomy. The precise distance measurements required for supernova studies have improved our understanding of the cosmic distance scale and helped resolve long-standing debates about the age and size of the universe. The statistical methods developed to analyze large samples of supernovae have been adopted throughout astronomy for studying everything from stellar populations to galaxy evolution. The discovery also demonstrates the power of long-term astronomical surveys. The original detection of cosmic acceleration required observations of dozens of supernovae, but subsequent studies have analyzed thousands of these explosions to refine our understanding. This kind of systematic large-scale approach to astronomy has become increasingly important as technology has made it possible to observe vast numbers of objects across the entire sky. Looking toward the future, Hubble continues to play a vital role in dark energy research. Even as newer space telescopes like the James Webb Space Telescope join the effort. Hubble's unique capabilities, particularly its stability and well-understood instrument characteristics, make it invaluable for the long-term monitoring programs needed to detect subtle changes in cosmic expansion. The telescope's 3-decade baseline of observations provides a crucial foundation for understanding how the universe has changed over time. The discovery of dark energy through Hubble's observations of distant supernovae represents one of the most important scientific breakthroughs of the past century. It has fundamentally changed our understanding of the universe and opened up entirely new fields of research. Yet it also reminds us how much we still don't know about the cosmos and suggests that even more surprising discoveries may be waiting for us as we continue to explore the universe with increasingly powerful tools and techniques. While Hubble was revolutionizing our understanding of the universe's expansion and dark energy, it was simultaneously making discoveries much closer to home that would completely change how we think about planets and the possibility of life beyond Earth. The same precision that allowed the telescope to measure distant supernovae also opened up an entirely new field of astronomy: the study of planets orbiting other stars. Before Hubble, we only knew about the planets in our own solar system. The idea that other stars might have planets was purely theoretical, and detecting them seemed almost impossible. These exoplanets, as they're called, are incredibly difficult to spot because they're so much dimmer than the stars they orbit. It's like trying to see a firefly next to a searchlight from hundreds of miles away. But Hubble's incredible sensitivity and stability made it possible to detect these distant worlds using several ingenious techniques. The most successful method Hubble uses is called transit photometry. This works by monitoring the brightness of stars over long periods of time, looking for tiny, regular dips in their light output. When a planet passes in front of its star from our perspective, it blocks a small fraction of the star's light, causing a temporary dimming that Hubble can detect. The amount of dimming tells us how big the planet is compared to its star, while the timing of these events reveals the planet's orbital period and distance from its star. What makes this technique so powerful is that Hubble can measure brightness changes as small as 1 part in 10,000. That means if a star normally produces 10,000 units of light, Hubble can detect when it drops to 9,999 units. This incredible precision is essential because even large planets cause very small dimming events. A planet the size of Jupiter orbiting a Sun-like star will only block about 1% of the star's light, while an Earth-sized planet blocks just 1/100th of 1%. But Hubble doesn't stop at just detecting these planets. The telescope can actually analyze what their atmospheres are made of by studying the light that passes through them during transits. When a planet moves in front of its star, some of the star's light filters through the planet's atmosphere before reaching us. Different gases in the atmosphere absorb specific wavelengths of light, creating a unique fingerprint that Hubble can detect using its spectrographs. This technique, called transmission spectroscopy, has allowed Hubble to identify water vapor, hydrogen, helium, sodium, carbon monoxide, carbon dioxide, and methane in the atmospheres of distant planets. Each of these detections represents a remarkable achievement, considering these planets are hundreds or thousands of light-years away. The telescope has even detected clouds and hazes in some exoplanet atmospheres, revealing weather patterns on worlds orbiting distant stars. One of Hubble's most significant contributions has been studying hot Jupiters, massive gas planets that orbit extremely close to their stars. These worlds are completely unlike anything in our solar system, with surface temperatures exceeding 2,000 degrees Celsius and years that last just a few Earth days. Some of these planets are so hot that their atmospheres are literally boiling away into space, and Hubble has been able to observe this atmospheric escape in real time. The telescope detected hydrogen atoms streaming away from several hot Jupiters, creating enormous comet-like tails of escaping gas. In some cases, these planets are losing millions of tons of atmosphere every second. This discovery revealed that planetary atmospheres are not permanent features, but can be dramatically altered or even completely stripped away by their host stars. It also showed that the intense radiation from nearby stars can fundamentally change a planet's composition and evolution. Hubble has also studied cooler exoplanets with more Earth-like temperatures, though these are much more challenging to observe because their transit signals are smaller and their atmospheres absorb less light. The telescope has detected water vapor in the atmospheres of several potentially habitable worlds, including planets orbiting in the habitable zones of their stars where liquid water could exist on their surfaces. One particularly intriguing discovery came from studying the TRAPPIST-1 system, which contains 7 Earth-sized planets orbiting a small, cool star just 39 light-years away. Hubble observations revealed that several of these planets likely have atmospheres, and some may even have substantial amounts of water. This system represents one of the best laboratories for studying potentially habitable worlds beyond our solar system. The telescope has also made unexpected discoveries about planetary formation and migration. Traditional theories suggested that large gas planets should form far from their stars, where it's cold enough for ice to condense, providing the solid cores needed to accumulate massive atmospheres. But Hubble's observations revealed many giant planets orbiting extremely close to their stars, often closer than Mercury orbits our Sun. These discoveries forced astronomers to develop new theories about how planetary systems form and evolve. It appears that many planets don't stay in the orbits where they originally formed, but instead migrate inward or outward over millions of years due to gravitational interactions with the disk of gas and dust from which they formed. Some hot Jupiters may have originally formed as far from their stars as Saturn is from our Sun, before spiraling inward to their current positions. Hubble has even detected planets in the process of formation, observing young stellar systems surrounded by disks of gas and dust where planets are actively condensing. These protoplanetary disks show gaps and spiral patterns that indicate planets are already forming and carving out their orbital paths through the surrounding material. By studying these young systems, astronomers can better understand how our own solar system formed 4.5 billion years ago. The telescope has also contributed to understanding planetary demographics, helping determine how common different types of planets are throughout the galaxy. By combining Hubble's detailed atmospheric studies with the planet discoveries from other telescopes like Kepler and TESS, astronomers have learned that planetary systems are incredibly diverse. Some stars host multiple small rocky planets packed close together, while others have one or two giant planets in distant orbits. Some systems are remarkably similar to our own, while others are completely alien in their architecture. One of the most surprising discoveries has been that super-Earths, planets between 1.5 and 4 times Earth's mass, are extremely common throughout the galaxy, even though our solar system doesn't contain any planets in this size range. These worlds represent a completely new category of planet that we had no idea existed before exoplanet discoveries began. Hubble has studied the atmospheres of several super-Earths, revealing that some have thick, hydrogen-rich atmospheres while others may be more like scaled-up versions of Earth or Venus. The telescope has also detected the first exoplanet moon candidate, though this discovery remains controversial and requires further confirmation. If verified, this would open up an entirely new category of potentially habitable worlds, as large moons orbiting giant planets could provide stable environments for liquid water and possibly life. Hubble's exoplanet discoveries have also revealed the incredible variety of stellar environments where planets can exist. The telescope has found planets orbiting binary star systems, where worlds experience sunrises from 2 different suns. It has detected planets around white dwarf stars, the dense remnants of dead stars, showing that some worlds can survive even when their host stars reach the end of their lives. There are planets orbiting pulsars, rapidly spinning neutron stars that emit beams of radiation, creating some of the most extreme environments imaginable. The atmospheric studies conducted by Hubble have also provided crucial insights into climate and weather on distant worlds. The telescope has detected wind speeds exceeding 2,000 miles per hour on some hot Jupiters, driven by the extreme temperature differences between their day and night sides. Some of these planets are tidally locked to their stars, meaning one side always faces the star while the other side remains in permanent darkness, creating extreme temperature gradients that drive powerful atmospheric circulation. Hubble has even detected what appears to be rain on some exoplanets, though not water rain as we know it. On some of the hottest worlds, the telescope has found evidence for clouds made of silicate particles, essentially tiny grains of sand and rock suspended in the atmosphere. When these clouds condense and precipitate, it would create literal sandstorms raining down on the planet's surface. The telescope's long-term monitoring capabilities have also allowed astronomers to study how exoplanet atmospheres change over time. Some worlds show variations in their atmospheric composition that might be related to seasonal changes, volcanic activity, or other dynamic processes. These observations provide insights into how planetary atmospheres evolve and what factors determine whether a world can maintain stable, potentially habitable conditions. Perhaps most importantly, Hubble's exoplanet discoveries have demonstrated that planetary systems are common throughout the galaxy. Nearly every star appears to host at least one planet, and many have multiple worlds in complex orbital arrangements. This suggests that the building blocks for planetary formation are widespread and that the processes that created our solar system have been repeated billions of times throughout cosmic history. The telescope continues to push the boundaries of what's possible in exoplanet science. New techniques are constantly being developed to extract more information from Hubble's observations, including methods to study the temperature structure of exoplanet atmospheres, detect atmospheric circulation patterns, and even search for possible signs of biological activity in the form of gases that might be produced by living organisms. These discoveries have also highlighted the importance of understanding our own planet's atmosphere and climate system. By studying the wide variety of atmospheric compositions and climate patterns on exoplanets, scientists gain new perspectives on the factors that make Earth habitable and how fragile these conditions might be. The extreme atmospheres observed on some exoplanets serve as natural laboratories for testing our understanding of atmospheric physics under conditions impossible to replicate on Earth. The field of exoplanet science that Hubble helped create has grown exponentially since the first discoveries. What began as a handful of unusual hot Jupiter detections has expanded into a comprehensive understanding of planetary system architecture, atmospheric composition, and the incredible diversity of worlds that exist throughout the galaxy. Each new discovery adds another piece to the puzzle of how planets form, evolve, and potentially develop the conditions necessary for life. The same techniques that allowed Hubble to detect planets around nearby stars also opened a window into something far more profound: the ability to look back through cosmic time and watch galaxies being born. While studying individual exoplanets required focusing on specific stars for weeks or months, understanding galaxy formation demanded a completely different approach. Hubble needed to stare at seemingly empty patches of space for hundreds of hours, collecting every photon of light from the most distant and ancient objects in the universe. This ambitious project began in 1995 when astronomers made what seemed like a crazy decision. They pointed Hubble at a tiny region of sky in the constellation Ursa Major that appeared to contain absolutely nothing. No bright stars, no obvious galaxies, just empty black space. For 10 consecutive days, Hubble collected light from this patch of sky that was smaller than a grain of sand held at arm's length. Many people thought this was a waste of precious telescope time, but the results completely revolutionized our understanding of the early universe. When the images from this Hubble deep field were finally processed, they revealed over 3,000 galaxies in what had appeared to be empty space. Each of these galaxies contained billions of stars, and because of their incredible distances, we were seeing them as they existed billions of years ago when the universe was much younger. It was like opening a photo album of the universe's childhood, revealing what galaxies looked like when cosmic history was just getting started. The most striking thing about these ancient galaxies was how different they looked from the large, organized, spiral and elliptical galaxies we see nearby today. The early galaxies were much smaller, more chaotic, and irregularly shaped. Many appeared to be in the process of merging or colliding with their neighbors. Instead of the neat spiral arms we associate with galaxies like the Milky Way, these primordial systems looked more like cosmic train wrecks, with stars scattered in random patterns and no clear organizational structure. This observation provided the first direct visual evidence for what astronomers call hierarchical structure formation. According to this theory, the universe started with small fluctuations in the distribution of matter, and these tiny variations grew over time through gravitational attraction. Small clumps of matter merged to form larger clumps, which eventually became the first stars and galaxies. These early galaxies then collided and merged with each other to build the massive galactic structures we see today. Hubble's deep field images showed this process in action. The telescope captured galaxies at various stages of merger, from systems that were just beginning to interact gravitationally to others that were in the final stages of combining into larger structures. Some images showed long streams of stars being pulled from smaller galaxies by the gravitational influence of their larger neighbors, creating spectacular tidal tails that stretched across millions of light years. Following the success of the original Hubble Deep Field, astronomers conducted similar observations in other parts of the sky. The Hubble Deep Field South looked at the southern hemisphere, while the Hubble Ultra Deep Field pushed even deeper, collecting light for over 11 days to reveal galaxies that were even more distant and ancient. Each successive observation revealed galaxies from earlier and earlier epochs in cosmic history, allowing astronomers to trace the evolution of galactic structures across more than 13 billion years. These ultra-deep observations revealed that galaxy formation was most active during a period astronomers call cosmic noon, which occurred roughly 10 to 12 billion years ago when the universe was between 2 and 4 billion years old. During this era, galaxies were forming stars at rates 10 to 100 times higher than what we observe in nearby galaxies today. The universe was a much more violent and active place, with intense bursts of star formation lighting up the cosmos. The images also revealed the changing nature of star formation over cosmic time. In the early universe, massive stars dominated the stellar populations of young galaxies. These giant stars burn through their nuclear fuel quickly and die in spectacular supernova explosions after just a few million years. The high rate of massive star formation in early galaxies meant they were constantly being rocked by supernova explosions, which heated their gas to millions of degrees and drove powerful winds that could blow material completely out of the galaxy. Hubble observations showed how this process of stellar feedback shaped early galaxy evolution. The telescope detected numerous examples of galactic superwinds, streams of hot gas being expelled from young galaxies at speeds of thousands of kilometers per second. These winds carried away much of the raw material needed for continued star formation, causing star formation rates to decline over time as galaxies exhausted their gas supplies. The deep field observations also revealed the role of galaxy mergers in building larger structures. Hubble captured numerous examples of galaxies in various stages of collision, from widely separated pairs just beginning to interact to systems in the final stages of merger where the original galaxies could barely be distinguished. These mergers weren't gentle affairs. Computer simulations based on Hubble observations showed that when galaxies collide, their gravitational interactions can trigger massive bursts of star formation as gas clouds are compressed and heated. Major galaxy mergers also appeared to be responsible for creating the supermassive black holes that Hubble found at the centers of most large galaxies. When two galaxies merge, their central black holes eventually spiral toward each other and combine into an even larger black hole. During this process, enormous amounts of gas fall into the merging black holes, causing them to shine brilliantly as quasars. Hubble observations revealed that quasar activity was much more common in the early universe, consistent with the higher merger rates during that epoch. The telescope also documented how galaxy morphology, or shape, evolved over cosmic time. In the nearby universe, most large galaxies fall into two main categories: spiral galaxies with organized disk structures and spiral arms, and elliptical galaxies that are more round or oval-shaped with no clear internal structure. But in the early universe, most galaxies were irregulars that didn't fit neatly into either category. Hubble observations showed that spiral galaxies like the Milky Way are relatively recent developments in cosmic history. The organized disk structures that characterize modern spirals require billions of years to develop, and they're easily disrupted by galaxy mergers. This explains why spiral galaxies are common in the nearby universe but rare among the most distant galaxies that Hubble observed. Elliptical galaxies, on the other hand, appear to form primarily through major galaxy mergers. When two spiral galaxies of roughly equal mass collide, the result is typically a large elliptical galaxy. Hubble's deep field observations provided snapshots of this transformation process, showing systems in various stages of merger that would eventually become the giant elliptical galaxies we observe in nearby galaxy clusters. The telescope also revealed dramatic differences in the sizes of galaxies over cosmic time. Early galaxies were not only more irregularly shaped, but also much more compact than their modern counterparts. A galaxy that contained as many stars as the Milky Way might have been packed into a region 10 times smaller in the early universe. This compactness had important implications for star formation and galaxy evolution, as stars were much closer together and interactions between them were more frequent. Hubble's observations showed that galaxies have grown not only by merging with other galaxies, but also by accreting matter from their surroundings. The telescope detected evidence for cold gas streams flowing into early galaxies, providing the raw material for continued star formation. These accretion streams were predicted by theoretical models but had never been directly observed before Hubble's sensitive instruments made them visible. The deep field observations also revealed the cosmic web structure of the universe on the largest scales. By mapping the positions of thousands of distant galaxies, Hubble showed that they're not randomly distributed throughout space, but instead form a vast network of filaments and walls separated by enormous voids. This large-scale structure reflects the initial distribution of dark matter in the early universe and provides crucial tests for cosmological models. Perhaps most remarkably, Hubble's deep field observations pushed back the frontier of the observable universe to within just a few 100 million years of the Big Bang. The most distant galaxies detected in these images existed when the universe was less than 1 billion years old, during an epoch when the first galaxies were just beginning to form. These primordial systems were much smaller and fainter than later galaxies, but they represented the seeds from which all subsequent cosmic structure would grow. The telescope revealed that even these earliest galaxies had already begun producing heavy elements through stellar nucleosynthesis. Spectroscopic observations detected the signatures of oxygen, carbon, and other elements that could only have been created inside stars and dispersed through supernova explosions. This showed that the first generation of stars had already lived and died by the time these early galaxies formed, enriching the universe with the building blocks necessary for planet formation and eventually life. Hubble also discovered that galaxy formation wasn't a smooth, gradual process, but instead occurred in fits and starts. Some early galaxies went through periods of intense star formation followed by long, quiet phases when very few new stars were born. This episodic behavior was likely driven by the complex interplay between star formation, supernova feedback, and gas accretion from the surrounding intergalactic medium. The observations revealed intriguing connections between galaxy properties and their environments. Galaxies in dense regions where many other galaxies were nearby tended to be more massive and showed signs of earlier star formation cessation. In contrast, galaxies in more isolated regions continued forming stars for longer periods. This environmental dependence provided important clues about the physical processes that control galaxy evolution. By combining observations of galaxies at different cosmic epochs, Hubble allowed astronomers to construct evolutionary sequences showing how individual galaxies change over billions of years. These sequences revealed that most large galaxies went through a phase of rapid growth early in their histories, followed by a gradual decline in star formation as they exhausted their gas supplies or expelled it through stellar feedback. The deep field observations also provided crucial constraints on the overall evolution of star formation in the universe. By counting the number of actively star-forming galaxies at different epochs and measuring their star formation rates, Hubble helped establish that the cosmic star formation rate peaked around 10 billion years ago and has been declining ever since. This finding had important implications for understanding when most of the stars in the universe formed and how the chemical composition of the cosmos has evolved over time. These discoveries fundamentally changed how astronomers think about galaxy formation and evolution. Rather than being static, unchanging objects, galaxies are now understood to be dynamic systems that have undergone dramatic transformations throughout cosmic history. The chaotic, star-forming irregulars that dominated the early universe gradually evolved into the organized spiral and elliptical galaxies we see today through a complex interplay of mergers, accretion, and internal physical processes. As Hubble revealed how galaxies evolved through mergers and violent transformations over billions of years, it also uncovered the driving force behind much of this cosmic violence. Supermassive black holes lurking at the centers of these galactic systems. These weren't the stellar mass black holes that form when individual stars collapse, but monsters containing millions or even billions of times more mass than our Sun, somehow packed into regions smaller than our solar system. The first hints that these cosmic giants existed came from observations of incredibly bright objects called quasars, which appeared to be single points of light that outshone entire galaxies. For decades, astronomers couldn't figure out what could possibly generate so much energy from such a compact source. The answer turned out to be supermassive black holes actively feeding on surrounding matter, heating it to millions of degrees and causing it to shine brighter than billions of stars combined. But proving that these black holes actually existed required more than just detecting bright quasars. Hubble's exceptional resolution and stability made it possible to measure the motion of stars and gas very close to the centers of nearby galaxies, looking for the telltale signs of an incredibly massive but invisible object. The telescope could track individual stars orbiting near galactic centers and measure their velocities with extraordinary precision. When Hubble looked at the galaxy M87, located about 55 million light-years away, it found something remarkable. Stars near the galaxy's center were moving at speeds exceeding 1,000 kilometers per second, far faster than could be explained by the gravitational influence of the visible stars alone. The only way to account for these extreme velocities was the presence of an object containing more than 3 billion solar masses crammed into a region smaller than our solar system. This was the smoking gun evidence that supermassive black holes really existed. The measurements were so precise that astronomers could actually map out how the gravitational field changed with distance from the galactic center, confirming that the mass was concentrated in an incredibly small region exactly as predicted for a black hole. Similar observations of other nearby galaxies revealed that almost every large galaxy harbored one of these monsters at its center. What made these discoveries even more intriguing was the realization that there seemed to be a fundamental relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge of stars. Galaxies with more massive bulges consistently had more massive central black holes, with the black hole typically containing about 0.1% of the bulge's total mass. This relationship held across an enormous range of galaxy masses, from dwarf galaxies with black holes containing just thousands of solar masses to giant ellipticals with black holes exceeding 10 billion solar masses. This correlation suggested that black hole growth and galaxy evolution were intimately connected, even though the black hole represented only a tiny fraction of the galaxy's total mass. Somehow, processes occurring in the immediate vicinity of the black hole could influence star formation and gas dynamics across the entire galaxy, spanning regions millions of times larger than the black hole itself. Hubble observations revealed the mechanism behind this connection by studying active galactic nuclei, galaxies where the central black holes were actively feeding on surrounding material. When matter falls toward a black hole, it doesn't plunge straight in, but instead forms a swirling accretion disk, spiraling inward while heating up through friction. As this material reaches temperatures of millions of degrees, it emits intense radiation across the electromagnetic spectrum. But the influence of feeding black holes extends far beyond just producing bright light. Hubble detected powerful jets of material being expelled from the immediate vicinity of supermassive black holes at speeds approaching the speed of light. These jets can extend for hundreds of thousands of light years beyond the host galaxy, carrying enormous amounts of energy into the surrounding space. The telescope captured spectacular images of these jets in action, showing how they carved through the intergalactic medium like cosmic blowtorches. In some cases, the jets created enormous bubbles of hot gas that could be seen in X-ray images, demonstrating that black holes were injecting vast amounts of energy into their host galaxies and beyond. This energy injection could heat the surrounding gas so much that it became unable to cool down and form new stars, effectively shutting down star formation across large regions of the galaxy. This process, known as AGN feedback, where AGN stands for active galactic nucleus, appeared to explain why the most massive galaxies in the universe had stopped forming stars billions of years ago. These giant elliptical galaxies contain mostly old red stars with very little ongoing star formation, despite containing enormous reservoirs of gas that should be able to form new stars. Hubble observations showed that many of these galaxies had active or recently active supermassive black holes that had heated their gas to such high temperatures that star formation became impossible. The telescope also revealed that black hole feeding isn't a steady process, but occurs in dramatic outbursts separated by long periods of relative quiet. Hubble detected evidence for these feeding episodes by observing light echoes, where pulses of radiation from past black hole activity illuminated surrounding gas clouds years or decades later. These observations allowed astronomers to study black hole outbursts that had occurred long before the telescope was even built. One of the most remarkable aspects of supermassive black holes that Hubble helped uncover was their role in galaxy mergers. When two galaxies collide, their central black holes eventually spiral toward each other in a cosmic dance that can last for millions of years. During the final stages of this merger process, enormous amounts of gas are funneled toward the black holes, triggering some of the most energetic events in the universe. Hubble captured images of galaxies in various stages of this merger process, showing how the gravitational interactions during galaxy collisions could trigger intense starbursts, while simultaneously feeding the central black holes. The telescope observed systems where both black holes were actively accreting material, creating dual-active galactic nuclei that would eventually merge into an even more massive black hole. The final merger of two supermassive black holes would produce gravitational waves, ripples in spacetime that were predicted by Einstein's theory of general relativity, but only directly detected for the first time in 2015 using ground-based detectors. However, these detectors can only observe the mergers of stellar mass black holes. The gravitational waves from supermassive black hole mergers have wavelengths thousands of times longer and require space-based detectors or pulsar timing arrays to detect. Hubble's observations of galaxy mergers provided crucial predictions for what these future gravitational wave detectors should find. By counting the rate of galaxy mergers at different epochs in cosmic history, astronomers could estimate how often supermassive black hole mergers should occur and how massive the resulting black holes should be. The telescope also revealed that not all supermassive black holes are created equal. While most appear to be spinning relatively slowly, some are rotating at nearly the maximum rate allowed by physics, spinning so fast that their event horizons are dramatically distorted from perfect spheres. These rapidly spinning black holes can extract energy from their own rotation through a process called the Penrose mechanism, potentially powering some of the most energetic jets observed in the universe. Hubble observations showed that the orientation of black hole jets provided clues about the spin direction of the central black hole. In some cases, the jets appeared to be aligned with the rotation axis of the host galaxy, suggesting that the black hole's spin was influenced by the large-scale structure of the galaxy. In other cases, the jets pointed in completely random directions, indicating that the black hole's spin was determined by more local processes such as recent merger events. The telescope also discovered that supermassive black holes could exist in much smaller galaxies than previously thought. Early surveys focused on the largest, most massive galaxies because their black holes were easier to detect. But as Hubble's instruments became more sensitive and observing techniques improved, astronomers found black holes in increasingly smaller and less massive systems. Some of the most surprising discoveries came from observations of dwarf galaxies, systems containing only a few billion stars compared to the hundreds of billions in galaxies like the Milky Way. Hubble detected several cases where these small galaxies contained black holes with masses of hundreds of thousands or even millions of solar masses, representing a much larger fraction of the galaxy's total mass than seen in larger systems. These observations raised important questions about how supermassive black holes formed in the early universe. In large galaxies, it's relatively easy to understand how black holes could grow from stellar mass seeds through accretion and mergers over billions of years. But in small galaxies with limited star formation, it's much harder to explain how black holes could reach such large masses. One possibility is that some supermassive black holes form directly from the collapse of primordial gas clouds in the early universe, bypassing the normal stellar evolution process entirely. These primordial black holes could have served as seeds that grew through accretion to become the supermassive black holes we observe today. Hubble observations of the most distant quasars provided some support for this idea, showing that billion solar mass black holes existed when the universe was less than 1 billion years old. The telescope also revealed the complex relationship between black hole growth and the chemical evolution of galaxies. Active galactic nuclei can both enhance and suppress the production of heavy elements by influencing star formation rates and driving gas flows within galaxies. In some cases, black hole jets appeared to trigger star formation by compressing nearby gas clouds, while in other cases they heated the gas so much that star formation was completely shut down. Hubble observations showed that the most massive black holes tended to be found in galaxies with the oldest stellar populations and the highest concentrations of heavy elements. This suggested that black hole growth and stellar nucleosynthesis proceeded hand in hand during the most active phases of galaxy evolution, with both processes contributing to the chemical enrichment of the cosmos. The telescope also provided insights into how black holes might have influenced the large-scale structure of the universe. By heating the gas within galaxy clusters, active galactic nuclei could prevent this material from cooling and forming new galaxies, potentially explaining why galaxy formation was less efficient in the densest regions of the universe. Long-term monitoring with Hubble revealed that supermassive black holes could remain active for millions or even billions of years, but their activity levels varied dramatically over much shorter timescales. Some black holes showed rapid flickering in their brightness over periods of hours or days, indicating that the accretion process was highly turbulent and variable. These observations provided crucial tests for theoretical models of black hole accretion. The rapid variability implied that the emission was coming from very close to the black hole's event horizon, where the extreme gravitational field causes dramatic changes in the properties of space and time. By studying these variations in detail, astronomers could probe the physics of matter under the most extreme conditions possible in the universe. Hubble also discovered that some supermassive black holes appeared to have been ejected from their host galaxies entirely, possibly as a result of gravitational wave recoil during black hole mergers. These wandering black holes could be detected through their gravitational influence on nearby stars or through the accretion of interstellar material as they moved through space. The cumulative impact of Hubble's black hole discoveries has been to show that these objects are not just exotic curiosities but fundamental components of galaxy evolution. Rather than being passive residents at galactic centers, supermassive black holes actively shape the properties of their host galaxies through feedback processes that operate across enormous ranges of space and time. Understanding this relationship has become crucial for explaining how galaxies acquired their observed properties and why galaxy formation was less efficient than simple gravitational collapse models would predict. While supermassive black holes represent the ultimate endpoint for the most massive objects in the universe, Hubble has also provided an extraordinary view of how stars begin and end their lives, revealing the complete cycle that transforms simple hydrogen gas into the complex elements that make planets and life possible. The same processes that feed black holes and shape galaxies also govern the birth and death of individual stars, and Hubble's cameras have captured these cosmic events in unprecedented detail. Star formation begins in vast clouds of gas and dust called molecular clouds, some of which can be hundreds of light years across and contain enough material to create thousands of new stars. These clouds are incredibly cold, with temperatures just a few degrees above absolute zero, and they're mostly invisible to optical telescopes because the dust grains suspended throughout them absorb and scatter visible light. But Hubble's ability to observe in infrared wavelengths allows it to peer through this cosmic fog and see what's happening inside. The telescope has revealed that star formation isn't a gentle, gradual process, but rather a violent and chaotic affair. Within these molecular clouds, gravity slowly pulls material together into increasingly dense clumps. But the process is far from smooth because these clouds are turbulent, with gas moving in complex swirling patterns driven by stellar winds, supernova explosions, and other energetic events in the surrounding region. Hubble observations have shown that the trigger for star formation often comes from external sources. A nearby supernova explosion can send a shockwave racing through a molecular cloud, compressing the gas and causing it to collapse more rapidly. The telescope has captured images of these shock fronts as they plow through star-forming regions, creating bright walls of ionized gas that mark the boundary between the expanding supernova remnant and the undisturbed interstellar medium. Once gravity takes over and a region of the molecular cloud begins to collapse, the process accelerates rapidly. As the gas falls inward, it heats up due to compression, and the collapsing region becomes what astronomers call a protostar. Hubble has observed hundreds of these objects in various stages of formation, showing how they gradually heat up and begin to glow as gravitational energy is converted into thermal energy. The most spectacular star-forming regions that Hubble has studied are places like the Eagle Nebula, home to the famous Pillars of Creation. These towering columns of gas and dust are being sculpted by radiation and stellar winds from nearby massive stars that formed earlier. The intense ultraviolet light from these hot stars ionizes the surrounding hydrogen gas, causing it to glow with a characteristic red color while simultaneously evaporating the outer layers of the gas pillars. But within these pillars, protected from the harsh radiation by the surrounding dust, new stars continue to form. Hubble images reveal dense knots of material called Bok globules, dark silhouettes against the brighter background where individual stars or small groups of stars are condensing. These globules are stellar nurseries in miniature, each containing enough material to create one or a few new stars. The telescope has also revealed the crucial role that magnetic fields play in star formation. As gas clouds collapse under their own gravity, any magnetic field threading through the material gets compressed and amplified. These magnetic fields can provide support against gravitational collapse, slowing down the star formation process and helping to determine the final mass of the resulting stars. Hubble observations of polarized light from dust grains aligned by magnetic fields have allowed astronomers to map the magnetic field structure in star-forming regions. Once a protostar accumulates enough mass and its core temperature reaches about 10 million degrees, nuclear fusion begins. This marks the birth of a true star, as hydrogen nuclei begin fusing together to form helium, releasing enormous amounts of energy in the process. The outward pressure from this nuclear energy balances the inward pull of gravity, and the star settles into a stable phase that can last for millions or billions of years depending on its mass. But Hubble has shown that even this stable phase isn't completely peaceful. Young stars are often surrounded by disks of leftover material from their formation, and these circumstellar disks can be the birthplace of planetary systems. The telescope has imaged dozens of these protoplanetary disks, revealing complex structures including gaps, spirals, and asymmetries that indicate planets are already forming within them. The telescope has also captured the dramatic jets and outflows that young stars produce as they settle into their main sequence lives. These Herbig-Haro objects, named after the astronomers who first studied them, appear as bright knots and streamers of gas moving at speeds of hundreds of kilometers per second away from newly formed stars. The jets are thought to be produced by the interaction between the star's magnetic field and the surrounding accretion disk, and they play a crucial role in the star's evolution role in removing excess angular momentum from the system. As stars age, their evolution depends critically on their initial mass. Low-mass stars like our Sun can burn hydrogen in their cores for billions of years. but eventually they exhaust their nuclear fuel and begin a complex series of evolutionary phases. Hubble has observed stars in all of these phases, providing a comprehensive view of stellar death for stars that aren't massive enough to explode as supernovae. When a sun-like star runs out of hydrogen in its core, it begins fusing helium into heavier elements like carbon and oxygen. This phase is much shorter-lived and causes the star to expand dramatically, becoming what astronomers call a red giant. Hubble has captured images of red giant stars with extended atmospheres that can reach sizes larger than Earth's orbit, showing how these evolved stars lose mass through powerful stellar winds. The final fate of these intermediate mass stars is to expel their outer layers entirely, creating some of the most beautiful objects in the universe, planetary nebulae. Despite their name, these nebulae have nothing to do with planets. They were given this name by early astronomers because some of them appeared round and planet-like through small telescopes. Hubble has revealed the true complexity of these objects, showing intricate structures including rings, jets, knots, and asymmetrical patterns that reflect the complex physics of the mass loss process. The Ring Nebula, the Cat's Eye Nebula, and the Helix Nebula are among the most famous planetary nebulae that Hubble has studied in detail. Each shows a different aspect of how dying stars can sculpt the surrounding material into spectacular displays. The central white dwarf star, which is all that remains of the original star's core, continues to emit intense ultraviolet radiation that ionizes the expelled gas, causing it to glow in brilliant colors that depend on which elements are present. These observations have revealed that planetary nebulae are not just beautiful, but also crucially important for the chemical evolution of galaxies. The dying stars that create them have spent billions of years converting hydrogen and helium into heavier elements through nuclear fusion, and the planetary nebula phase is how these elements get distributed back into the interstellar medium where they can be incorporated into future generations of stars and planets. But for the most massive stars, those with more than about 8 times the mass of our Sun, the story ends very differently. These stellar giants burn through their nuclear fuel much more rapidly, sometimes in just a few million years, and their death throes are among the most violent events in the universe. Hubble has captured numerous examples of supernova explosions and their aftermath, showing how these cosmic bombs can outshine entire galaxies for weeks or months. The telescope observed the famous supernova 1987A in the Large Magellanic Cloud, a nearby galaxy where a massive star exploded and became visible to the naked eye. Hubble's long-term monitoring of this explosion revealed the complex interaction between the supernova shockwave and the material that the star had expelled during its lifetime. The images showed bright rings of gas lighting up as the supernova energy reached them, providing insights into the star's evolution during the thousands of years before it exploded. Supernova explosions are responsible for creating and dispersing most of the heavy elements in the universe. Elements heavier than iron can only be formed during the extreme conditions of a supernova explosion, when the tremendous energy and neutron flux can drive nuclear reactions that would be impossible under normal stellar conditions. Hubble observations of supernova remnants have allowed astronomers to study this nucleosynthesis process and understand how elements like gold, platinum, and uranium are created and distributed throughout space. The Crab Nebula represents one of the best-studied supernova remnants in the sky. This object formed from a star that exploded in the year 1054 and was recorded by Chinese astronomers as a guest star, bright enough to see during daylight. Hubble images show the complex filamentary structure of the expanding gas cloud, which continues to glow nearly 1,000 years after the original explosion. At the center of the nebula lies a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. Neutron stars represent another possible endpoint for stellar evolution. These objects are incredibly dense, packing more mass than the Sun into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh as much as a mountain on Earth. Hubble has contributed to our understanding of these exotic objects by studying the nebulae that surround them and the effects of their intense magnetic fields on the surrounding material. The telescope has also revealed the role of stellar winds throughout a star's lifetime. Even during their stable main sequence phase, stars lose mass through stellar winds, streams of charged particles flowing away from their surfaces. For the most massive stars, these winds can be so powerful that they strip away significant fractions of the star's mass over its lifetime, affecting both the star's evolution and its eventual fate. Hubble observations have shown that stellar winds from massive stars can carve out enormous cavities in the surrounding interstellar medium, creating what astronomers call stellar wind bubbles. These hot, low-density regions can extend for hundreds of light-years around the most massive stars, and they play an important role in heating and stirring the gas between stars. The telescope has also studied Wolf-Rayet stars, extremely massive and evolved stars that are losing mass at tremendous rates. These objects can lose the equivalent of Earth's mass every year through their powerful stellar winds, enriching the surrounding space with heavy elements even before they explode as supernovae. Hubble images of Wolf-Rayet stars show the complex shells and rings of material they've expelled, creating spectacular displays that reveal the star's evolutionary history. Brown dwarfs represent another category of objects that Hubble has helped to understand. These are objects that formed like stars but never accumulated enough mass to sustain nuclear fusion in their cores. They're sometimes called failed stars, and they occupy the boundary between the smallest true stars and the largest planets. Hubble's infrared sensitivity has been crucial for studying these cool, dim objects and understanding how the star formation process can produce objects across a wide range of masses. The telescope has also contributed to understanding stellar clusters, groups of stars that form together from the same molecular cloud. By studying clusters of different ages, astronomers can observe stars at various stages of their evolution and test theoretical models of stellar development. Hubble's exceptional resolution allows it to distinguish individual stars even in densely packed globular clusters that contain hundreds of thousands of stars. These cluster studies have revealed that star formation often occurs in bursts rather than at a steady rate. Young clusters show evidence for multiple generations of star formation, with successive waves of stellar birth triggered by the winds and supernova explosions from earlier generations. This feedback process regulates the overall efficiency of star formation and helps explain why only a small fraction of the gas in molecular clouds actually gets converted into stars. The complete picture of stellar evolution that Hubble has revealed shows how stars serve as the universe's chemical factories, converting the simple hydrogen and helium created in the Big Bang into the full periodic table of elements. This process of stellar nucleosynthesis is what makes planets like Earth possible, and ultimately enables the complex chemistry required for life. Every carbon atom in your body was forged in the core of a dying star, and every oxygen atom you breathe was expelled into space when that star reached the end of its life. While the elements forged in distant stars eventually became the building blocks for planets throughout the galaxy, Hubble has also served as our most reliable scout for exploring the worlds much closer to home. The same telescope that peers billions of years into the past has simultaneously revolutionized our understanding of our own solar system, acting as a complement to the spacecraft missions that visit these worlds up close. When most people think about Hubble, they imagine it studying distant galaxies and nebulae, but the telescope has actually spent a significant portion of its time observing our planetary neighbors. This might seem like using a Formula One race car to drive to the grocery store, but Hubble's unique capabilities make it incredibly valuable for solar system science in ways that aren't immediately obvious. The telescope's position above Earth's atmosphere gives it a crystal-clear view that ground-based telescopes simply can't match. Our atmosphere is constantly moving and turbulent, which blurs the images of even relatively nearby objects like planets. Hubble doesn't have to deal with atmospheric distortion, so it can capture incredibly sharp images that reveal details on planetary surfaces and in their atmospheres that would be impossible to see from the ground. One of Hubble's most important contributions to solar system science has been its long-term monitoring of the giant planets. Jupiter, Saturn, Uranus, and Neptune all have dynamic atmospheres that change dramatically over time scales ranging from hours to decades. Ground-based telescopes can capture snapshots of these changes, but Hubble has been able to provide consistent, high-quality observations over more than 3 decades, creating an unparalleled record of how these worlds evolve. Jupiter has been one of Hubble's most frequently observed targets, and the telescope has documented remarkable changes in the planet's famous Great Red Spot. This massive storm system, which is large enough to swallow Earth completely, has been shrinking steadily over the past century. When astronomers first measured it in the 1800s, the Great Red Spot was about 40,000 kilometers across. Hubble observations have shown that it's now less than half that size, and the shrinking appears to be accelerating. The telescope has also captured dramatic changes in Jupiter's atmospheric bands and zones. These alternating stripes of different colored clouds are created by powerful jet streams in Jupiter's atmosphere, and they're constantly shifting and changing. Hubble has observed the appearance of new storms, the merger of existing storm systems, and the complete disappearance of some atmospheric features that had been stable for decades. Perhaps most spectacularly, Hubble was perfectly positioned to observe the collision of comet Shoemaker-Levy 9 with Jupiter in July 1994. This comet had been torn apart by Jupiter's gravity during a previous close approach, creating a string of fragments that struck the planet over the course of several days. Hubble captured unprecedented images of the impacts, showing enormous fireballs and dark scars in Jupiter's atmosphere that were larger than Earth itself. These impact observations provided crucial insights into both the composition of comets and the structure of Jupiter's atmosphere. The dark scars left by the impacts revealed material from deeper layers of Jupiter's atmosphere that had been brought to the surface by the explosions. Spectroscopic analysis of these features allowed astronomers to measure the abundance of water, sulfur compounds, and other materials in Jupiter's atmosphere with unprecedented precision. The comet impacts also demonstrated Jupiter's role as a cosmic vacuum cleaner, protecting the inner solar system from potentially dangerous objects. Jupiter's enormous gravitational influence captures or deflects many comets and asteroids that might otherwise pose a threat to Earth. Hubble's observations of the Shoemaker-Levy 9 impacts provided direct evidence of this protective effect and helped scientists understand how Jupiter has shaped the evolution of the entire solar system. Saturn has also been a frequent target for Hubble observations, particularly its magnificent ring system. The telescope has monitored seasonal changes in the rings as Saturn's tilt relative to the Sun changes during its 29.5-year orbit. When the rings are tilted edge-on to Earth, they become almost invisible, But as Saturn's seasons progress, we see them from different angles, revealing new details about their structure and composition. Hubble discovered that Saturn's rings contain spokes, dark radial features that appear and disappear on time scales of hours. These spokes are thought to be created by electromagnetic forces that lift tiny dust particles above the main ring plane, but their exact formation mechanism is still not completely understood. The telescope's ability to monitor the rings continuously over long periods has been crucial for understanding these mysterious features. The telescope has also studied Saturn's many moons, particularly Titan, the largest moon in the Saturn system and the only moon in the solar system with a thick atmosphere. Hubble observations revealed seasonal changes in Titan's atmospheric haze and helped identify the presence of clouds in the moon's nitrogen-rich atmosphere. These observations provided important context for the Cassini-Huygens mission, which arrived at Saturn in 2004 and eventually landed a probe on Titan's surface. Uranus and Neptune, the two outermost giant planets, are much more difficult to study because of their enormous distances from Earth, but Hubble's sensitivity and stability have allowed it to make important discoveries about these ice giant worlds. The telescope detected new moons around both planets and provided detailed maps of their atmospheric features, including massive storm systems that can cover significant portions of their surfaces. One of the most surprising discoveries was the detection of aurorae on both Uranus and Neptune. These planets have complex magnetic fields that are tilted at large angles relative to their rotation axes, creating auroral displays that are very different from those we see on Earth or Jupiter. Hubble's ultraviolet instruments were able to detect the faint glow of these aurorae, providing insights into the magnetic field structures of these distant worlds. Mars has been another major target for Hubble observations, serving as an early warning system for dust storms and providing global context for the rovers and orbiters studying the planet's surface. The telescope can monitor weather patterns across Mars's entire hemisphere, tracking the development and evolution of dust storms that can sometimes engulf the entire planet. These global dust storms occur roughly every 2 Earth years when Mars is closest to the Sun in its elliptical orbit. The increased solar heating can trigger local dust storms that sometimes grow to planetary scale, obscuring the surface for months at a time. Hubble observations have been crucial for understanding how these storms develop and spread, information that's essential for planning rover operations and orbital missions. The telescope has also monitored Mars's polar ice caps as they grow and shrink with the Martian seasons. Mars has a much more elliptical orbit than Earth, and its axial tilt is similar to Earth's, creating seasonal changes that are more extreme than what we experience. Hubble has documented how the polar caps advance and retreat, revealing details about the planet's climate and atmospheric circulation patterns. Venus, despite being our closest planetary neighbor, is one of the most challenging worlds to study because of its thick atmosphere and complete cloud cover. But Hubble's ability to observe in ultraviolet wavelengths has revealed circulation patterns in Venus's upper atmosphere that are invisible at other wavelengths. The telescope has tracked the movement of cloud features and measured wind speeds in the planet's atmosphere, contributing to our understanding of the runaway greenhouse effect that makes Venus the hottest planet in the solar system. Mercury, the innermost planet, is extremely difficult to observe from Earth because it's always close to the Sun in our sky. But during rare transits, when Mercury passes directly in front of the Sun as seen from Earth, Hubble has been able to make precise measurements of the planet's size and orbital characteristics. These observations have contributed to tests of Einstein's general relativity by measuring the precession of Mercury's orbit with extraordinary precision. Beyond the major planets, Hubble has made important contributions to asteroid science. The telescope has observed hundreds of asteroids, measuring their sizes, shapes, rotation periods, and compositions. These observations have revealed that asteroids are incredibly diverse objects, ranging from solid, monolithic rocks to loose collections of rubble barely held together by gravity. One of the most significant asteroid discoveries made by Hubble was the detection of water vapor around the dwarf planet Ceres. This was the first definitive evidence for water activity on any object in the asteroid belt, suggesting that Ceres might have a subsurface ocean similar to some of the moons of Jupiter and Saturn. This discovery helped guide the Dawn mission, which arrived at Ceres in 2015 and confirmed the presence of water ice and possibly even liquid water beneath the dwarf planet's surface. Hubble has also contributed to our understanding of potentially hazardous asteroids that could pose a threat to Earth. The telescope's precise astrometric capabilities allow it to track the orbits of these objects with extraordinary accuracy, helping to determine whether they might impact Earth in the future. In several cases, Hubble observations have been crucial for ruling out potential impacts that initially appeared possible based on less precise ground-based observations. The telescope has studied comets throughout the solar system, from short-period comets that orbit the Sun every few years to long-period comets that take thousands of years to complete their orbits. These observations have revealed the diverse compositions and structures of these icy visitors from the outer solar system. Hubble has detected water vapor, carbon dioxide, carbon monoxide, and various organic compounds in comet atmospheres, providing insights into the conditions in the early solar system when these objects formed. One particularly interesting discovery was the detection of oxygen and hydrogen around Comet 67P Churyumov-Gerasimenko, the target of the European Space Agency's Rosetta mission. Hubble observations showed that this comet was producing water vapor at a much higher rate than expected, information that was crucial for planning Rosetta's approach and landing sequence. The telescope has also studied the Kuiper Belt, the region beyond Neptune's orbit that contains thousands of icy objects left over from the solar system's formation. These Kuiper Belt objects, or KBOS, are incredibly difficult to study because they're so small and distant, but Hubble's sensitivity has allowed astronomers to detect and characterize hundreds of them. The most famous KBO that Hubble has studied is Pluto, which was still classified as the 9th planet when many of the observations were made. The telescope discovered 4 of Pluto's 5 known moons and helped determine that Pluto and its largest moon, Charon, form a binary system where both objects orbit around a common center of mass located between them. Hubble observations also revealed that Pluto's surface is more complex and varied than anyone expected. Maps created from the telescope's observations showed distinct bright and dark regions on Pluto's surface, suggesting a diverse geological history. These observations provided crucial information for planning the New Horizons mission, which flew past Pluto in 2015, confirmed many of Hubble's predictions about the dwarf planet's surface features. The telescope has even detected atmospheres around some of the largest KBOS, including Eris and Makemake. These distant objects are so cold that most of their atmospheres should be frozen on their surfaces, but sublimation of ices can create thin atmospheres that Hubble can detect through careful spectroscopic observations. Perhaps most remarkably, Hubble has served as a pathfinder for many of the solar system missions that followed. The telescope's observations of Jupiter helped plan the Galileo mission's trajectory and scientific observations. Its studies of Saturn provided crucial context for the Cassini mission. Mars observations have guided rover operations and orbital surveys. In each case, Hubble's global perspective and long-term monitoring capabilities have provided information that no other observatory could obtain. The telescope's role in solar system science demonstrates how astronomical observations work best when different types of missions and instruments work together. Spacecraft can provide incredibly detailed close-up views of individual worlds, but Hubble offers the global perspective and long-term stability needed to understand how these worlds change over time. Ground-based telescopes can provide frequent observations, but they lack the resolution and spectroscopic capabilities that Hubble offers from above Earth's atmosphere. As new solar system missions continue to launch and new discoveries are made, Hubble remains an essential tool for putting these findings into context and monitoring the ongoing evolution of our planetary neighborhood. The telescope's 3 decades of solar system observations have created an invaluable database of information about how planets, moons, asteroids, and comets behave over timescales that no single mission could hope to cover. While studying our nearby planetary worlds provided crucial insights into how solar systems work, understanding the true scale of the universe required Hubble to tackle one of astronomy's most fundamental challenges: accurately measuring distances to far-off objects. Without reliable distance measurements, astronomers couldn't determine whether a distant galaxy was actually enormous or just appeared large because it was closer than expected. This problem of cosmic distance measurement had plagued astronomy for decades, but Hubble's exceptional capabilities finally provided the precision needed to build a reliable distance scale that extends from our cosmic neighborhood all the way to the edge of the observable universe. The foundation of this cosmic distance ladder rests on a special type of star called a Cepheid variable. These stars pulsate regularly, getting brighter and dimmer in cycles that can last anywhere from a few days to several months. The key discovery that made Cepheid so useful for distance measurement was made by Henrietta Swan Leavitt in the early 1900s. She found that there's a direct relationship between how long a Cepheid takes to complete one pulsation cycle and how intrinsically bright it actually is. This relationship works because Cepheids pulsate due to a specific physical process happening in their interiors. As the star expands and contracts, the opacity of its outer layers changes, which affects how much light can escape. Stars with higher luminosity have longer pulsation periods because it takes more time for the pulsations to travel through their larger interiors. Once you know this relationship, you can observe any Cepheid variable, measure its pulsation period, and immediately know how bright it should be intrinsically. The beauty of this method is that once you know how bright a star should be and you can measure how bright it appears in the sky, simple physics tells you exactly how far away it must be. If a star appears dimmer than it should, it must be farther away because light spreads out as it travels through space, becoming dimmer with distance according to the inverse square law. Before Hubble, ground-based telescopes could only identify Cepheid variables in the nearest galaxies, and even then the measurements were often uncertain due to atmospheric interference and limited resolution. But Hubble's sharp vision and stability revolutionized Cepheid observations. The telescope could clearly distinguish individual Cepheid stars in galaxies up to 100 million light-years away, providing precise distance measurements that were impossible to obtain from the ground. One of Hubble's first major projects was to observe Cepheids in the Virgo cluster, a massive collection of galaxies located about 54 million light-years from Earth. This cluster contains over 1,000 galaxies, making it one of the nearest large galaxy clusters and therefore crucial for calibrating the cosmic distance scale. By identifying dozens of Cepheid variables in several Virgo cluster galaxies, Hubble was able to determine the cluster's distance with unprecedented accuracy. These measurements immediately resolved a long-standing controversy in astronomy. Different methods for measuring cosmic distances had been giving conflicting results, leading to what astronomers called the distance scale crisis. Some techniques suggested the universe was relatively young, around 8 billion years old, while others indicated it was much older, perhaps 15 billion years. Hubble's precise Cepheid distances helped resolve this crisis by providing a solid foundation that other distance measurement methods could be calibrated against. The telescope's Cepheid observations also played a crucial role in determining the Hubble constant, which describes how fast the universe is expanding. This fundamental constant relates the recession velocity of galaxies to their distances, and knowing its precise value is essential for determining the age and ultimate fate of the universe. By measuring accurate distances to galaxies at various distances, Hubble provided the data needed to calculate the Hubble constant with much greater precision than had ever been achieved before. But Cepheids can only be observed out to distances of about 100 million light-years, even with Hubble's exceptional capabilities. Beyond that distance, individual stars become too faint to detect reliably, so astronomers need other methods to measure even greater distances. This is where the cosmic distance ladder concept becomes crucial. Each rung of the ladder extends farther into space but must be calibrated using the more reliable methods that work at shorter distances. Hubble helped establish the next rung of the distance ladder by studying Type Ia supernovae, the same stellar explosions that later led to the discovery of dark energy. These supernovae are incredibly useful as distance indicators because they all reach approximately the same peak brightness when they explode. This happens because Type Ia supernovae occur when a white dwarf star in a binary system accumulates material from its companion until it reaches a critical mass of about 1 4/10 times the mass of the Sun. At this point, the white dwarf undergoes runaway nuclear fusion and explodes completely. Because all Type Ia supernovae involve white dwarfs of essentially the same mass exploding in the same way, they all release similar amounts of energy and reach similar peak brightnesses. This makes them excellent standard candles for measuring cosmic distances, but only if we know exactly how bright they should be. This is where Hubble's Cepheid observations became crucial. By finding Type Ia supernovae in galaxies where Cepheids had already provided accurate distance measurements, astronomers could calibrate the absolute brightness of these stellar explosions. Hubble observed dozens of Type Ia supernovae in galaxies with known Cepheid distances, allowing astronomers to determine that these explosions reach a peak absolute magnitude of about -19.3. This calibration meant that astronomers could then use Type Ia supernovae to measure distances to galaxies billions of light-years away, far beyond the reach of Cepheid observations. The telescope also contributed to understanding the subtle variations among Type Ia supernovae that affect their usefulness as distance indicators. Not all of these explosions are exactly identical, and astronomers discovered relationships between the explosion characteristics and the peak brightness that allow for more precise distance measurements. Brighter supernovae tend to rise to maximum light more slowly and decline more gradually, while fainter ones evolve more rapidly. By measuring these light curves carefully, astronomers can determine small corrections that make Type Ia supernovae even more reliable distance indicators. Surface brightness fluctuations represent another distance measurement technique that Hubble helped develop and refine. This method relies on the statistical properties of star formation in galaxies. When you look at a nearby galaxy, you can see individual bright stars that create a grainy, fluctuating appearance in the galaxy's light. But in more distant galaxies, these individual stars blend together into a smooth distribution. By measuring the amount of graininess or fluctuation in a galaxy's surface brightness, astronomers can determine how far away it must be. Hubble's exceptional resolution made this technique practical for measuring distances to galaxies throughout the local universe. The telescope could detect the subtle brightness fluctuations in galaxies out to distances of about 160 million light-years, providing an independent check on distances measured using other methods. This technique proved especially valuable for studying elliptical galaxies, which often don't contain the young, bright stars needed for Cepheid observations. The telescope also helped establish the planetary nebula luminosity function as a distance indicator. Planetary nebulae, the glowing shells of gas expelled by dying stars, have a characteristic maximum brightness that appears to be similar in different galaxies. By identifying the brightest planetary nebulae in distant galaxies and comparing their apparent brightness to the known maximum brightness, astronomers can estimate distances. Hubble's ability to identify these small, faint objects in distant galaxies made this technique much more reliable than had been possible with ground-based observations. For the most distant galaxies, beyond the reach of individual star observations, Hubble contributed to developing techniques based on the fundamental properties of galaxies themselves. The Tully-Fisher relation connects the rotation speed of spiral galaxies to their intrinsic brightness. Galaxies that rotate faster tend to be more massive and therefore more luminous. By measuring the width of spectral lines, which reveals how fast a galaxy is rotating, and comparing this to the galaxy's apparent brightness, astronomers can estimate its distance. Hubble observations helped calibrate this relationship by studying nearby galaxies with known distances and measuring their rotation speeds with high precision. The telescope's spectroscopic capabilities allowed astronomers to measure galaxy rotation curves with unprecedented detail, revealing how the relationship between rotation speed and luminosity depends on galaxy type, star formation rate, and other galactic properties. The surface brightness test provided another way to measure distances to the most remote galaxies. This technique is based on the idea that objects of the same physical size should appear smaller and dimmer as they get farther away, but their surface brightness should remain constant if the universe is not expanding. In an expanding universe, however, the surface brightness of distant objects should decrease because their light is redshifted to longer wavelengths and their apparent size is affected by cosmic expansion. Hubble's deep field observations provided crucial data for testing this relationship by measuring the surface brightness of galaxies at various redshifts. These measurements confirmed that the universe is indeed expanding and provided independent evidence for the cosmological models developed from other observations. The telescope also contributed to understanding gravitational lensing as a distance measurement tool. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravitational field bends the light path, creating multiple images or distorted arcs. The amount of distortion depends on the masses and distances of both the lensing object and the background source. By modeling these lensing effects carefully, astronomers can determine distances to both the lens and the background object. Time delay measurements in gravitationally lensed systems provide another distance indicator that Hubble helped develop. When a variable object like a quasar is lensed into multiple images, changes in brightness don't occur simultaneously in all images because light takes different amounts of time to travel along the different light paths. By measuring these time delays and modeling the lens geometry, astronomers can determine the distance to the lensed object. Hubble monitored several gravitationally lensed quasars over periods of years, measuring the time delays between brightness variations in different lensed images. These observations provided independent distance measurements that could be compared with other techniques, helping to validate the cosmic distance scale and test cosmological models. The cumulative result of all these distance measurement techniques has been the construction of a cosmic distance ladder that astronomers have high confidence in. Each rung of the ladder has been carefully calibrated against the others, and multiple independent methods often give consistent results for the same objects. This consistency provides strong evidence that the distance scale is fundamentally correct. Hubble's distance measurements have had profound implications for our understanding of cosmology. The precise determination of the Hubble constant led to a much more accurate estimate of the universe's age, 13.8 billion years. This resolved the earlier crisis, where some distance measurements suggested the universe was younger than its oldest stars, which would have been impossible. The telescope's distance measurements also revealed that the geometry of space is very close to flat, meaning that parallel lines remain parallel even over cosmic distances. This finding was crucial for constraining cosmological models and understanding the relative amounts of matter, and dark energy in the universe. Long-term monitoring with Hubble has also revealed that the Hubble constant might not actually be constant over time. Recent measurements suggest that the expansion rate in the nearby universe is slightly higher than what would be predicted based on observations of the cosmic microwave background radiation from the early universe. This discrepancy, known as the Hubble tension, might indicate that our understanding of cosmic expansion is incomplete, or that there are unknown physical processes affecting the universe's evolution. The precision of Hubble's distance measurements has reached the point where systematic errors and subtle physical effects become important considerations. The telescope's observations have revealed that dust extinction, metallicity variations, and stellar population differences can all affect distance measurements in ways that must be carefully accounted for to achieve percent-level accuracy. Despite these challenges, the cosmic distance ladder that Hubble helped construct remains one of the greatest achievements in observational astronomy. It has transformed our understanding of the universe's scale, age, and evolution, providing the foundation for modern cosmology and our current understanding of dark energy and the universe's ultimate fate. The telescope's 3 decades of distance measurements have created a legacy that will continue to influence astronomy for generations to come. Building this precise cosmic distance ladder required Hubble to peer through vast regions of space filled with gas, dust, and complex structures that most people think of as empty vacuum. But the space between stars and galaxies is far from empty, and Hubble's observations have revealed these cosmic clouds as some of the most beautiful and scientifically important objects in the universe. These nebulae, from the Latin word for cloud, represent active cosmic recycling centers, where the products of stellar death become the raw materials for future generations of stars and planets. The most visually striking nebulae are the emission nebulae, glowing clouds of gas that shine with their own light. These cosmic light shows are powered by nearby hot stars that emit intense ultraviolet radiation. When this high-energy light hits hydrogen atoms in the surrounding gas clouds, it strips away their electrons in a process called ionization. When these electrons eventually recombine with the hydrogen nuclei, they emit light at very specific wavelengths, creating the characteristic red glow that dominates most emission nebulae. Hubble has captured breathtaking images of emission nebulae throughout our galaxy, revealing intricate structures that ground-based telescopes could never resolve clearly. The Orion Nebula, one of the most photographed objects in the sky, appears completely transformed when viewed through Hubble's cameras. What looks like a simple glowing cloud from Earth reveals itself as an incredibly complex region with cavities, filaments, shock fronts, and dense knots of gas where new stars are actively forming. The telescope's images of the Orion Nebula have shown how the intense radiation and stellar winds from young, massive stars sculpt the surrounding gas into elaborate structures. The four brightest stars at the nebula's heart, known as the trapezium, are extremely hot and emit such powerful ultraviolet radiation that they've carved out a large cavity in the surrounding molecular cloud. The walls of this cavity glow brilliantly as the stellar radiation ionizes the gas, creating the spectacular display we observe. But Hubble's observations revealed that this isn't a static picture. The nebula is constantly changing as stellar winds and radiation pressure continue to push against the surrounding gas. The telescope has detected shock fronts moving through the nebula at speeds of tens of kilometers per second, heating the gas to thousands of degrees and creating the complex filamentary structures that give emission nebulae their characteristic appearance. The Eagle Nebula, home to the famous Pillars of Creation, represents another spectacular example of how stellar radiation shapes the interstellar medium. These towering columns of gas and dust stretch for several light years and are being gradually eroded by ultraviolet radiation from nearby massive stars. Hubble's images show the intricate detail of this erosion process, with streamers of gas being blown away from the pillar surfaces while dense cores remain protected in their shadows. What makes these observations scientifically valuable beyond their obvious beauty is that they reveal the complex physics governing star formation and the dispersal of heavy elements throughout space. The pillars themselves are stellar nurseries, dense regions where gravity is pulling material together to form new stars. But the same radiation that makes the nebula glow is also working to destroy these star-forming regions by heating and dispersing the gas. Hubble has captured this cosmic tug-of-war between star formation and destruction in dozens of star-forming regions throughout our galaxy. The telescope's ability to observe in multiple wavelengths simultaneously has allowed astronomers to map the temperature, density, and chemical composition of the gas in these regions with unprecedented detail. The chemical composition data has been particularly revealing. Different elements emit light at different wavelengths when they're ionized, creating spectral lines that serve as fingerprints for specific atoms and molecules. Hubble's spectrographs can detect these lines and measure their relative strengths, allowing astronomers to determine exactly what elements are present and in what quantities. These measurements have shown that nebulae are far from uniform in their composition. Elements like oxygen, nitrogen, and sulfur, which are produced inside stars through nuclear fusion, are not evenly mixed throughout the interstellar medium. Instead, they show complex patterns that reflect the history of stellar winds, supernova explosions, and gas flows that have shaped each region over millions of years. Planetary nebulae, despite their misleading name, represent a completely different type of nebula that Hubble has studied extensively. These objects form when intermediate mass stars like our Sun reach the end of their lives and expel their outer layers into space. The remaining stellar core, now a white dwarf, is extremely hot and ionizes the expelled gas, causing it to glow in the same way as emission nebulae. But planetary nebulae show an incredible diversity of shapes and structures that emission nebulae typically don't display. Hubble has revealed planetary nebulae that look like rings, butterflies, hourglasses, and even more exotic shapes that defy easy description. The Ring Nebula appears as an almost perfect circle when viewed from Earth, but Hubble's detailed observations revealed that it's actually a complex three-dimensional structure with knots, jets, and multiple shells of expelled material. The Cat's Eye Nebula showcases even more complexity, with concentric shells, symmetrical jets, and intricate knots that create a pattern resembling a cosmic flower. Hubble observations showed that the central white dwarf had multiple episodes of mass loss, each creating a different shell structure. The symmetrical patterns suggest that magnetic fields or binary companion stars played important roles in shaping the expelled material. These complex structures in planetary nebulae have provided crucial insights into the final stages of stellar evolution. The shapes and patterns reveal how stars lose mass during their red giant phases, and how stellar winds, magnetic fields, and orbital motions all contribute to sculpting the expelled material. Many planetary nebulae show clear evidence for bipolar structures, suggesting that most of their central stars are actually binary systems where interactions with a companion star influence the mass loss process. Supernova remnants represent another category of nebula that Hubble has studied in extraordinary detail. These expanding shells of hot gas mark the locations where massive stars ended their lives in catastrophic explosions. The Crab Nebula, the remnant of a supernova that was observed by Chinese astronomers in 1054, shows the ongoing interaction between the explosion debris and the surrounding interstellar medium. Hubble images of the Crab Nebula reveal a complex web of filaments expanding outward at speeds of over 1,000 kilometers per second. These filaments are heated to temperatures of tens of thousands of degrees by the shock wave from the original explosion, causing them to glow in the light of various ionized elements. The telescope's spectroscopic observations have identified the signatures of hydrogen, helium, oxygen, sulfur, and many other elements that were either present in the original star or created during the explosion itself. The Veil Nebula represents the remnant of a much older supernova explosion that occurred roughly 8,000 years ago. Hubble observations show how this ancient blast wave continues to plow through the interstellar medium, heating and compressing the gas it encounters. The intricate filamentary structure reveals the complex three-dimensional geometry of the expanding shock front and how it interacts with variations in the density of the surrounding medium. These supernova remnant observations have been crucial for understanding how heavy elements get distributed throughout space. The explosions don't just create heavy elements through nuclear reactions during the blast itself, they also disperse the elements that were created inside the star during its lifetime. Oxygen, silicon, iron, and other metals that are essential for planet formation and life are scattered across vast regions of space by these explosions. Dark nebulae represent a completely different type of cosmic cloud that Hubble has helped astronomers understand. These regions appear dark not because they don't contain any material, but because they contain so much dust that they block the light from background stars. The famous Horsehead Nebula in Orion is a classic example of a dark nebula silhouetted against a bright emission nebula background. Hubble's infrared capabilities have allowed astronomers to peer through the dust in these dark nebulae and see what's happening inside them. Many dark nebulae turn out to be active star-forming regions where new stars are condensing from the surrounding gas and dust. The dust that makes these regions appear dark in visible light actually plays a crucial role in star formation by helping gas clouds cool down and collapse under their own gravity. The telescope has revealed that dark nebulae often contain complex internal structures, including dense cores, filaments, and cavities carved out by stellar winds from newly formed stars. These observations have shown that star formation is a highly organized process, with gas flowing along filamentary structures toward dense nodes where stars eventually form. Reflection nebulae add yet another category to the nebula zoo. These clouds don't emit their own light, but instead reflect and scatter light from nearby stars. The scattered light tends to be bluer than the original starlight because blue light scatters more efficiently than red light, the same process that makes Earth's sky appear blue. Hubble has captured stunning images of reflection nebulae that appear as ghostly blue wisps surrounding young star clusters. The telescope's observations have revealed that many nebulae actually combine multiple types in the same object. The Trifid Nebula, for example, contains both emission and reflection components, with the red emission region powered by hot stars and the blue reflection region created by dust scattering starlight. These complex nebulae provide laboratories for studying how different physical processes interact in the interstellar medium. Herbig-Haro objects represent a special class of nebulae associated with the very earliest stages of star formation. These are jets and shock fronts created when newly forming stars expel material at high speeds. Hubble has observed dozens of these objects, showing how young stellar jets plow through the surrounding molecular cloud material, creating bow shocks and other structures as they interact with the ambient gas. The telescope's time-lapse observations of Herbig-Haro objects have actually captured their motion, showing how these jets evolve and change over periods of just a few years. This represents some of the fastest celestial motion that can be directly observed, with some features moving at apparent speeds of hundreds of kilometers per second. Hubble observations have also revealed the crucial role that stellar winds play in shaping nebulae throughout their evolution. Even during their main sequence lifetimes, stars continuously lose mass through stellar winds, streams of charged particles flowing away from their surfaces. For the most massive stars, these winds can be so powerful that they create enormous cavities in the surrounding interstellar medium. Wolf-Rayet stars, extremely massive and evolved stars that are losing mass at tremendous rates, create some of the most spectacular wind-blown nebulae. Hubble has observed numerous examples of these stars surrounded by complex shells and rings of material they've expelled. The telescope's spectroscopic capabilities have allowed astronomers to trace the chemical composition of this expelled material, showing how these stars enrich their surroundings with heavy elements even before they explode as supernovae. The long-term stability of Hubble's instruments has made it possible to study how nebulae change over time. While most changes occur too slowly to be noticeable over human timescales, some of the most active regions show measurable evolution over the telescope's 3-decade lifetime. The expanding shells around some planetary nebulae have grown measurably larger, while shock fronts in supernova remnants have advanced through the surrounding medium. These temporal studies have provided direct observational evidence for theoretical models of how nebulae evolve and interact with their surroundings. The observations have confirmed that the interstellar medium is a dynamic, ever-changing environment where the products of stellar evolution are continuously mixed and recycled to form new generations of stars and planets. The cumulative picture that has emerged from Hubble's nebular observations is one of a galaxy filled with active, interconnected recycling systems. Gas and dust flow from star-forming regions to evolved stars and back again in complex cycles that operate over millions of years. Heavy elements created in stellar interiors are dispersed throughout space by stellar winds and supernova explosions, gradually enriching the interstellar medium and making possible the formation of rocky planets and the complex chemistry required for life. The complex recycling processes that create and shape these spectacular nebulae depend on something that most people can't see or directly detect, yet it dominates the gravitational landscape of the universe. While the glowing gas and dust in nebulae represent the visible matter we can observe directly, there's something else out there that's much more abundant and mysterious. Hubble has played a crucial role in mapping this invisible substance called dark matter by using one of Einstein's most profound predictions, that massive objects can bend space itself and act like cosmic magnifying glasses. This phenomenon, called gravitational lensing, occurs because gravity doesn't just pull on matter, it actually warps the fabric of space-time itself. When light travels through this warped space, it follows the curves and bends just like a marble rolling across a stretched rubber sheet would follow the depressions created by heavy objects placed on the sheet. From our perspective, this makes distant galaxies appear distorted, magnified, or even split into multiple images when a massive object lies between us and the background source. Hubble's exceptional image quality and stability made it the perfect instrument for detecting and studying these gravitational lensing effects. The telescope could identify the subtle distortions in galaxy shapes that reveal the presence of intervening mass, even when that mass is completely invisible. This capability opened up an entirely new way of studying the universe's dark matter distribution and provided some of the most compelling evidence that this mysterious substance actually exists. The first strong gravitational lenses that Hubble studied were dramatic cases where background galaxies appeared as nearly perfect rings around massive foreground objects. These Einstein rings, named after the physicist who predicted them, occur when the lensing mass, the background source, and the observer are almost perfectly aligned. The ring shape represents the distorted and magnified image of a single background galaxy that's been stretched into a circle by the gravitational field of the intervening mass. But most gravitational lensing effects are much more subtle than these spectacular Einstein rings. Hubble observations revealed that virtually every massive galaxy cluster acts as a gravitational lens, creating weak distortions in the shapes of hundreds or thousands of background galaxies. These weak lensing effects are so small that they're barely detectable even with Hubble's superb image quality. But when measured statistically across large numbers of background galaxies, they provide a powerful probe of the mass distribution in the foreground cluster. The key insight that made weak lensing so valuable for dark matter studies was the realization that the lensing effects depend on the total mass of the intervening object, not just the visible mass that we can see in stars and gas. When Hubble measured the lensing distortions around galaxy clusters, astronomers could create detailed maps showing exactly where all the mass was located, including both the visible matter that shows up in ordinary photographs and the invisible dark matter that can only be detected through its gravitational effects. These mass maps revealed something remarkable. The majority of the mass in galaxy clusters isn't located where the visible galaxies are. Instead, it's distributed in a more extended, smoother pattern that encompasses much larger volumes than the visible matter. In most clusters, the dark matter outweighs the visible matter by a factor of about 5 to 1, meaning that 80% of the cluster's mass is completely invisible except for its gravitational influence. One of the most dramatic demonstrations of dark matter's existence came from Hubble observations of the Bullet Cluster, a system where two galaxy clusters had collided and passed through each other. During this cosmic collision, the hot gas that fills the space between galaxies in each cluster was slowed down and heated by the collision, creating a bright X-ray emission that shows where most of the visible matter ended up after the crash. But the gravitational lensing maps told a different story. The strongest lensing effects, indicating where most of the mass was located, didn't coincide with the X-ray bright regions where the visible matter had accumulated. Instead, the lensing maps showed that most of the mass had passed right through the collision relatively unaffected, continuing in the same directions that the original galaxy clusters had been traveling before they met. This separation between the visible matter and the gravitational effects provided smoking gun evidence that dark matter really exists as a separate component that interacts differently with ordinary matter. The dark matter particles in each cluster barely interact with anything except through gravity, so they passed right through each other during the collision. The ordinary matter, however, consists of charged particles that can collide and transfer momentum, causing it to slow down and heat up during the impact. Hubble observations of dozens of galaxy cluster collisions have revealed similar patterns, consistently showing that the bulk of the mass in these systems behaves like dark matter rather than ordinary matter. These observations have provided crucial tests for dark matter theories and have helped rule out alternative explanations for the gravitational effects that don't involve invisible particles. The telescope has also contributed to understanding dark matter on smaller scales by studying gravitational lensing around individual galaxies. Even single galaxies can act as gravitational lenses, though the effects are much weaker than those produced by massive galaxy clusters. Hubble's sensitivity and image quality have made it possible to detect these galaxy-scale lensing effects and use them to measure the dark matter content of individual galaxies. These observations revealed that dark matter halos around galaxies extend much farther out than the visible stars and gas. While the stars in a typical spiral galaxy might extend out to a radius of 50,000 light-years, the dark matter halo can reach distances of several 100,000 light-years. This extended dark matter distribution explains why the outer regions of galaxies rotate faster than would be expected based on the visible matter alone, resolving a puzzle that had confused astronomers for decades. Hubble has also studied gravitational lensing by dark matter substructures within galaxy clusters. Computer simulations of dark matter predict that large dark matter halos should contain numerous smaller subhalos, creating a complex hierarchical structure. The telescope's high-resolution images have been sensitive enough to detect lensing effects from these substructures, providing direct observational evidence for the clumpy distribution of dark matter predicted by theoretical models. One particularly intriguing aspect of Hubble's lensing observations has been the detection of dark matter concentrations that don't seem to contain any visible galaxies at all. These dark clumps, revealed only through their gravitational lensing effects, suggest that dark matter can form bound structures independently of ordinary matter. This finding has important implications for understanding how galaxies form and evolve within their dark matter halos. The telescope has also contributed to measuring the overall geometry and expansion history of the universe through gravitational lensing studies. The strength of lensing effects depends not only on the mass of the intervening object, but also on the distances between the lens, the source, and the observer. By studying lensing in galaxy clusters at different redshifts, corresponding to different epochs in cosmic history, Hubble has provided independent measurements of cosmological parameters that complement other methods for studying dark energy and cosmic expansion. Time delay measurements in multiply-lensed systems have provided another way for Hubble to probe cosmology and dark matter. When a variable source like a quasar is lensed into multiple images, brightness changes don't occur simultaneously in all images because light takes different amounts of time to travel along the different light paths created by the gravitational lens. The time delays depend on the mass distribution of the lens and the cosmological distances involved. Hubble has monitored several gravitationally lensed quasars over periods of years, measuring the time delays between brightness variations in different lensed images. These measurements provide independent determinations of the Hubble constant and other cosmological parameters, offering valuable cross-checks on results obtained through other methods like Cepheid variables and Type 1a supernovae. The telescope has also studied gravitational lensing by individual dark matter subhalos and satellite galaxies. These smaller-scale lenses can create detectable perturbations in the lensing patterns produced by galaxy clusters, allowing astronomers to count and characterize the population of dark matter substructures. These observations provide important tests for dark matter models and help constrain the properties of dark matter particles. Microlensing represents another type of gravitational lensing that Hubble has contributed to understanding. When a compact object like a star, planet, or dark matter clump passes directly in front of a background star, it can cause a temporary brightening as the gravitational field focuses the background star's light. While ground-based surveys have discovered thousands of microlensing events, Hubble's sharp resolution has been crucial for resolving the lensed images and extracting detailed information about the lensing objects. The telescope has also studied lensing by primordial black holes, hypothetical objects that could have formed in the early universe and might comprise some fraction of the dark matter. If primordial black holes exist in significant numbers, they should produce detectable microlensing signatures when they pass in front of background stars. Hubble observations have placed important constraints on the abundance of these objects across a wide range of masses. Strong lensing systems where background galaxies are stretched into giant arcs have provided natural telescopes that allow Hubble to study extremely distant and faint objects. The magnification provided by gravitational lensing can make background galaxies appear tens or hundreds of times brighter than they would without the lens, allowing detailed studies of galaxy properties at redshifts that would otherwise be impossible to observe. These lensed galaxy studies have revealed the properties of some of the earliest galaxies in the universe, showing how star formation, chemical enrichment, and galaxy assembly proceeded during the first billion years after the Big Bang. The high magnifications provided by gravitational lensing have allowed astronomers to study individual star-forming regions in galaxies that existed when the universe was less than 10% of its current age. Hubble has also contributed to understanding how dark matter properties affect structure formation on cosmic scales. Different dark matter models predict different patterns of structure formation, and gravitational lensing observations provide direct tests of these predictions. The telescope's measurements of dark matter distributions in galaxy clusters have helped distinguish between different types of dark matter particles and constrain their interaction properties. The statistical properties of weak lensing distortions measured by Hubble have provided powerful constraints on the total amount of dark matter in the universe and how it's distributed on large scales. These measurements have been crucial for establishing the standard cosmological model, which includes both dark matter and dark energy as major components of the universe's energy budget. Hubble observations have also revealed that dark matter distributions can be affected by feedback processes involving ordinary matter. When galaxies form stars or when supermassive black holes become active, they can drive powerful outflows that redistribute gas within their dark matter halos. These processes can alter the central density profiles of dark matter halos in ways that can be detected through gravitational lensing measurements. The telescope's long baseline of observations has also allowed studies of how dark matter structures evolve over cosmic time. By comparing lensing measurements of galaxy clusters at different redshifts, astronomers can track how the dark matter distribution has changed as the universe expanded and structures continued to grow through gravitational collapse. Perhaps most remarkably, Hubble's gravitational lensing observations have revealed that dark matter really does behave like a form of matter rather than a modification of gravitational physics. Alternative theories that attempt to explain galactic rotation curves and other phenomena without invoking dark matter particles generally predict different lensing signatures than those observed by Hubble. The detailed agreement between lensing observations and dark matter models provides strong evidence that dark matter consists of actual particles rather than being a manifestation of modified gravity. The cumulative impact of Hubble's gravitational lensing discoveries has been to establish dark matter as a crucial component of cosmic structure and to provide detailed maps of how this invisible substance is distributed throughout the universe. These observations have transformed dark matter from a theoretical speculation into an observational reality and have provided the foundation for our current understanding of how cosmic structure formation proceeds in a universe dominated by invisible matter. While dark matter provides the invisible scaffolding that holds cosmic structures together, understanding how galaxies actually function requires studying the vast reservoir of gas and dust that fills the space between their stars. This interstellar medium, as astronomers call it, was once thought to be mostly empty space with a few scattered atoms here and there. But Hubble's observations have revealed it as a complex, dynamic environment that plays a crucial role in every aspect of galactic evolution, from star formation to the recycling of heavy elements throughout cosmic history. The interstellar medium consists of several distinct phases that exist under different physical conditions and play different roles in galactic processes. The most obvious component is the cold, dense molecular gas where new stars form. But there's also warm ionized gas heated by stellar radiation and hot gas that's been heated to millions of degrees by supernova explosions and stellar winds. Hubble's ability to observe across multiple wavelengths has been essential for studying all these different components and understanding how they interact with each other. Cold molecular clouds represent the nurseries where star formation occurs, but they're incredibly difficult to study because they're so cold that they emit virtually no visible light. Temperatures in these clouds can drop to just 10 or 20 degrees above absolute zero, making them invisible to most astronomical instruments. However, these clouds contain dust grains that absorb starlight from background sources, creating the dark patches and lanes that Hubble can observe silhouetted against brighter regions. But Hubble's infrared capabilities allow it to peer through much of this dust and observe the warm emission from dust grains that have been heated by nearby stars. These observations have revealed that dust plays a much more important role in the interstellar medium than anyone initially realized. The dust grains serve as surfaces where atoms can stick together and form molecules, including the hydrogen molecules that make up the bulk of star-forming gas. The telescope has also studied how dust grains themselves evolve and change throughout their lifetimes. These microscopic particles form in the atmospheres of evolved stars and are expelled into space through stellar winds. Once in the interstellar medium, they can grow by accumulating additional atoms from the gas or be destroyed by shock waves from supernovae and stellar winds. Hubble observations have tracked these processes by studying the changing properties of dust in different environments. One of the most important discoveries about interstellar dust came from studying how it affects the light from distant stars and galaxies. Dust grains don't just block light uniformly across all wavelengths. Instead, they absorb and scatter blue light much more efficiently than red light, causing distant objects to appear redder than they actually are. This reddening effect had to be carefully accounted for in all of Hubble's distance measurements and studies of stellar populations. But the reddening observations also revealed information about the dust grains themselves. Different grain sizes and compositions produce different reddening patterns, allowing astronomers to determine the properties of dust in various parts of our galaxy and others. Hubble measurements showed that dust properties vary significantly from one region to another, reflecting different histories of star formation and supernova activity. The warm, ionized component of the interstellar medium fills much of the volume of galactic disks and represents material that's been heated and ionized by ultraviolet radiation from hot stars. This component has temperatures of around 10,000 degrees and densities that are much lower than the cold molecular gas. Hubble's ultraviolet spectroscopic capabilities have been crucial for studying this phase because many of the important diagnostic spectral lines occur at ultraviolet wavelengths that can't be observed from the ground. These ultraviolet observations revealed that the warm, ionized medium has a much more complex structure than anyone expected. Rather than being a uniform background, it shows intricate filamentary patterns and structures that reflect the complex interplay between stellar energy input and gas dynamics. The telescope detected numerous expanding shells and superbubbles created by the combined effects of stellar winds and supernova explosions from groups of massive stars. The hot component of the interstellar medium exists at temperatures of millions of degrees and was initially detected through X-ray observations. This gas has been heated by supernova shock waves and represents one of the primary ways that massive stars inject energy into their surroundings throughout their lifetimes and deaths. While Hubble can't observe this hot gas directly because it emits primarily X-rays, the telescope has studied the interfaces where this hot gas interacts with cooler components. These interaction regions often appear as glowing filaments where the hot gas is cooling down and condensing, creating spectacular structures that Hubble has imaged in great detail. The Veil Nebula and other supernova remnants show these cooling interfaces beautifully, revealing how energy from stellar explosions gradually dissipates into the surrounding interstellar medium over thousands of years. Hubble observations have also revealed the crucial role that magnetic fields play throughout the interstellar medium. While magnetic fields are invisible, they can be detected through their effects on polarized light from background stars or through the alignment of dust grains that get twisted by magnetic forces. These observations have shown that magnetic fields permeate the entire interstellar medium and play important roles in controlling the flow of gas and the formation of stars. The magnetic field structure appears to be closely related to the spiral arm patterns in galaxies, with field lines generally following the spiral structure but showing complex variations and reconnection events. In star-forming regions, magnetic fields can provide support against gravitational collapse, helping to regulate the rate at which new stars form. But they can also channel the flow of gas along field lines, creating the filamentary structures that are so prominent in Hubble images of molecular clouds. Stellar winds represent another crucial mechanism for stirring and heating the interstellar medium. Even during their stable main sequence lifetimes, stars continuously lose mass through stellar winds, but the properties of these winds vary dramatically depending on the star's mass, age, and evolutionary state. Hubble has studied stellar winds throughout the galaxy by observing their effects on surrounding gas and dust. Massive stars produce particularly powerful winds that can clear out large cavities in the surrounding interstellar medium. These stellar wind bubbles can extend for tens or hundreds of light years around the most massive stars, creating low-density regions filled with hot gas. When multiple massive stars form in the same region, their combined winds can create enormous superbubbles that can blow completely out of the galactic disk, allowing hot gas to escape into the surrounding galactic halo. Wolf-Rayet stars, which represent a late evolutionary phase for the most massive stars, produce some of the most extreme stellar winds in the galaxy. These stars can lose mass at rates equivalent to one Earth mass per year, creating spectacular nebulae as their winds interact with previously expelled material. Hubble has studied dozens of these systems, revealing complex shell structures that record the entire mass loss history of these evolved massive stars. The telescope's observations have also revealed how stellar winds enrich the interstellar medium with heavy elements produced through nuclear fusion in stellar interiors. Elements like carbon, nitrogen, oxygen, and silicon that are created inside stars get dispersed throughout the interstellar medium through stellar winds, even before the stars explode as supernovae. This gradual enrichment process has been crucial for the chemical evolution of galaxies over cosmic time. Supernova explosions represent the most dramatic way that stars inject energy and heavy elements into the interstellar medium. A single supernova can release as much energy in a few seconds as our Sun will produce over its entire 10 billion-year lifetime, and this energy goes into heating and accelerating the surrounding gas to incredible speeds. Hubble has studied supernova remnants at various stages of evolution, from young remnants where the shock front is still advancing through the surrounding medium to ancient remnants that have nearly merged with the general interstellar background. The Crab Nebula, formed by a supernova that occurred in 1054, shows how supernova energy continues to affect the interstellar medium nearly 1,000 years after the original explosion. The expanding shell of debris continues to sweep up and heat the surrounding gas, while the central pulsar, a rapidly spinning neutron star left behind by the explosion, continues to inject energy through relativistic particles and magnetic fields. Older supernova remnants, like the Veil Nebula, demonstrate how supernova energy eventually dissipates into the general interstellar medium. These ancient remnants have expanded to diameters of hundreds of light years and now move slowly enough that they're beginning to merge with the surrounding gas. The shock fronts have cooled sufficiently that they now emit primarily optical light rather than X-rays, creating the beautiful filamentary structures that make these objects such popular targets for astronomical imaging. Hubble observations of supernova remnants have also provided crucial information about the nucleosynthesis processes that occur during stellar explosions. Different elements produce characteristic spectral lines when they're heated and ionized by supernova shockwaves, allowing astronomers to map the distribution of various elements throughout the remnants. These observations have confirmed theoretical predictions about which elements are produced in different types of stellar explosions and how they get distributed throughout space. The chemical composition of the interstellar medium provides a record of all the stellar processes that have occurred throughout a galaxy's history. Hubble's spectroscopic capabilities have allowed detailed studies of the abundances of various elements in different parts of our galaxy and others, revealing gradients and patterns that reflect the history of star formation and stellar evolution. These abundance measurements show that the interstellar medium is not chemically uniform, but instead shows systematic variations that provide clues about galactic evolution. The central regions of galaxies tend to be more enriched in heavy elements than their outer regions, reflecting the higher rates of star formation and supernova activity that have occurred near galactic centers throughout cosmic history. Hubble has also studied how gas flows into and out of galaxies, processes that are crucial for understanding how galaxies acquire the material they need for continued star formation. The telescope has detected evidence for gas accretion from the intergalactic medium, showing how galaxies can continue growing by pulling in material from their surroundings. These accretion flows appear to be particularly important for maintaining star formation in large spiral galaxies like the Milky Way. Galactic winds represent the opposite process, where gas is expelled from galaxies by the combined effects of stellar winds, supernova explosions, and active galactic nuclei. Hubble has observed these outflows in numerous galaxies, showing how they can remove significant fractions of a galaxy's gas content and potentially shut down star formation. These winds also carry heavy elements out into the intergalactic medium, contributing to the chemical enrichment of the cosmic web. The telescope has revealed that galactic winds can have complex multi-phase structures, with hot gas moving at high speeds and cooler gas that's been accelerated by interactions with the hot component. These outflows can extend for tens of thousands of light-years beyond the visible parts of galaxies, creating enormous structures that affect the evolution of entire galaxy groups and clusters. Feedback processes involving the interstellar medium appear to be crucial for regulating star formation rates throughout cosmic history. If gas could collapse and form stars with perfect efficiency, galaxies would have converted all their gas into stars billions of years ago. But observations show that star formation is actually quite inefficient, with only a small percentage of available gas getting converted into stars in any given time period. This inefficiency appears to result from feedback processes where energy from massive stars heats and disperses the gas before it can form additional stars. Hubble observations of star-forming regions have shown how stellar winds and radiation pressure from newly formed massive stars can halt star formation in their immediate vicinity by heating and expelling the surrounding gas. This self-regulation helps explain why star formation rates have declined over cosmic time as gas reservoirs have been gradually depleted. The interstellar medium also serves as a crucial diagnostic tool for understanding the physics of galaxy collisions and mergers. When galaxies collide, the interactions between their interstellar media can trigger bursts of star formation, while also heating gas to such high temperatures that it gets stripped away entirely. Hubble has observed numerous examples of these processes in merging galaxy systems, showing how galactic interactions can dramatically alter the properties of the interstellar medium. Tidal tails and streams of gas that get pulled out during galaxy mergers represent some of the most spectacular examples of how gravitational interactions can reshape the interstellar medium. These structures can extend for hundreds of thousands of light-years and often show active star formation where the tidal forces have compressed the gas to sufficient densities for gravitational collapse to occur. The overall picture that has emerged from Hubble's studies of the interstellar medium is one of a highly dynamic system that's constantly being stirred, heated, and enriched by stellar processes, while simultaneously serving as the raw material for future generations of stars. This cosmic recycling system has operated for over 13 billion years, gradually transforming the simple hydrogen and helium created in the Big Bang into the complex mixture of elements that makes rocky planets and life possible. Understanding these processes has been crucial for developing our current picture of how galaxies form and evolve throughout cosmic history.